Good afternoon. And last class we have been talking about a new technique called algorithmic state machine or ASM for implementation of digital logic. As I had mentioned last time, it is not a new design technique. It is the same as the FSM using state machine, using state graphs, state table, and using flip-flops and things like that. But ASM is a slightly different way of drawing the state graph. That gives a little bit better feel for the type of system that we are going to design, especially from the point of view of hardware design. We saw a couple of examples. One was a general block diagram which we did not have any specific design in mind. We also saw the design of a multiplier. Today we will do one more example. This will be called, today's lecture I am calling it system design. See, now we have covered everything that is needed. Everything that is needed to design simple digital systems. Of course, you can also design the same knowledge is enough for even designing complicated circuits, but then that requires a little more of exposure to the type of components available and all that. And the state graph becomes very big and involved. So it may require little practice. That's why I call it simple design systems. But from the point of view of the requirements of knowledge, tools, we have everything. We have understood combination logic. We have understood the components of combination logic, how to design combination logic. We have also defined sequential logic, building blocks of sequential logic, various components available for sequential logic, and what a general system is. General system is a sequential logic with a combination logic which drives the flip-flops. So this background is there for us, so we should be able to, in practice, in theory, we should be at least able to design whatever digital system we have in mind. But again, as I said, we keep this system simple because the first elementary level course, we only exposed you to the basics of combination logic and sequential logic and finite state machines and digital system design. That is why I call it simple designs. We are capable of that. And from here to the next stage of more advanced machines is not very difficult if one spends time and reads up a little bit more. Conceptually, there is nothing new. Now, this time I am going to call it a traffic light control. Let us remember this block diagram that we did last time. Here is a digital system. We have two blocks. One is called data path, where the actual components of the system exist. In the case of multiplier example that we did last time, it consists of a adder, shift registers and everything. So data path has data input, data out, and we have what is known as the controller, which controls the operation based on the requirement of the system So the controller gives commands and monitors the status of the data path. So as soon as you are ready with the data path, you start giving commands based on the requirement sequentially, and then we see where we are by tracking the status of this data path to issue the commands next time. In addition, they may have some external inputs and external outputs. External input may be a simple thing like a start signal. An external output may be something like a light indicator. So this is divided by a clock. I will write the clock here, because otherwise the circuit becomes. There will also be a clock here. See, the clock is not exclusive to the data path, because controller, as we saw yesterday in the last lecture, controller also has flip-flops, which are driven by combination logic. Flip-flop driving logic is combinational, but there is a flip-flop which takes the controller from state to state for the operation of the required sequence of the digit system that we are designing. So this is the clock which is to be given. I don't know whether I forgot to put this clock in the last time, the block diagram. If I have not done it, please include it. Now, this background, we have done already a couple of examples. A simple example using an arbitrary sum, and an example of a multiplier, 4-bit multiplier, 5-bit multiplier, multiplicand multiplier are given. We know how to do the multiplication. What are the signals required? What is the data path required? What are the signals required to start and proceed? And then we also took the command back, status back. Today we are going to talk about a traffic light controller, another system. This is a complete system. This gives you an idea, because controller, multiplier is still a part of a computer or a calculator. So you will think that only such things can be designed using whatever knowledge you have gained in this course. That is why, to take you away from these things, I am taking an example of a traffic light controller. You can do several things like this. This is only an example. I can do a combination logic. I can do a video game, dice game, whatever you want. The traffic light controller will operate the lights at a traffic junction. Let me first draw supposing there is a main road. And then there is a side street. This is side. Since it has the left-turn traffic here, this is the direction in which the traffic will go in the main road. and in the side road. The side street traffic can take a left turn anytime, and the on a left turn here, and the main street traffic can take a left turn here anytime, or from here into this. I'm making this a very simple exercise. You can have a more complicated set of conditions. Right now I only have a main street and a side street. There may be more than one street. There may be a pedestrian crossing. There may be a left protected right turn. All that is possible, but we are not going to discuss all that now. I'm going to take a simple design. So there are now a set of lights here. One set of light for the main road traffic. Lights. And for the side street traffic, one set of lights here, and one set of lights here. So what are the various lights we want? We want main street, or main road. The traffic light is red, yellow, green, as we see, normal traffic lights. There are two of these. This is this direction. For this direction we have but we don't have to have two sets of lights. Actually these are parallel. This is connected to this is connected to this. For the side street we have for this traffic it is red, yellow, green. Again they are not two different set of lights, same set of lights parallel. So this is connected to this connected to this connected to this. So they are parallel lights. So what I am trying to say is I can control this light, this also gets controlled at the same time. When I control this light, this also gets controlled. Now what is the rule? What is that we want to design? So the problem statement. The problem statement starts right here. Problem statement is to design a traffic light control. First step is problem statement to design the traffic light control. exact specifications is given in this. So the problem statement continues. Normally, main road is green and the side street is red. If there is traffic waiting in the side street, and just because it is waiting, you won't allow every time, because we can't disturb the main street traffic so frequently, and is important. If a time t main green has elapsed, we go to main street yellow and side street is still red. Here main street is yellow because the traffic is slowing down. I can't afford to make the side street green, so it's still red. After T M yellow, after time T main yellow, main street becomes red and side street becomes green. After side green, time T side green. T side green, the side street is green only for a short time compared to the main street. If the main street green is 2 minutes, side street green maybe 1 minute or even less than that. After time TSG, main street becomes still red, side street becomes yellow. After time side street yellow, main street becomes green again and the side street becomes red. And the process continues. In fact, I will remove this condition now to start with. If there is a traffic waiting in the side street, let us assume traffic will be waiting in the way. We can introduce this condition later on to make it simpler. After time T main green. Now, so problem is simplified very much. There is a main road, there's a side road. Main road has red, green and red, yellow and green. Red, yellow and green. Side street has red, yellow, green, red, yellow, green. Normally traffic is in the main road. Side street traffic will be blocked. This will be red, this will be green, this will be red. But you can't afford to do it all the time, so we'll allow for certain time for this traffic, whatever is the time you want. After that, we'll make this yellow, but this will continue to be red, and then this will go on for some time for this traffic to slow down. Then after that time, this becomes red, this becomes red, this becomes green, this becomes green. Then side street will be green, main street traffic will be blocked. Now side street traffic takes place. After some time, which may be less than the main street green, this becomes yellow, this continues to be red. And after some time, when the traffic has slowed down sufficiently, you make this red and this green. And then you start all over again. Very simple. I can introduce conditions like after the elapse of certain time, if the traffic is, there's no traffic, you can put a car sensor. If the car sensor is not active, there's no point in stopping the main road traffic. I can also have a pedestrian switch. If the pedestrian switch is pressed, it should stop the traffic. I can also say we are only now able to turn left, turn left, turn left, turn left. I can also make turn right possible. In that case, the opposite traffic should be stopped. Similarly, from here, turn right, opposite traffic should be blocked. All those conditions I am not putting now, the initial, earlier version, simpler version. So the next step is, this is problem statement in great detail. Now, next is the data path. What are the components required? Data path is nothing but the components required and what are the inputs and outputs of the components. These are off-the-shelf components. For example, the last time multiplier, we took a adder, registers, some of them shift registers. We took a counter, and the counter was counting from n to 0. When 0 was there is a comparator. That Z was the output that went to the controller. All those things are data path. Like that here, this data path is going to be very simple. We need lights. I need lights. I need red, green, red, yellow, green lights. How many? 4 each. Because 2 for the main road, 2 for the side road, each of these. Then I need a timer. I said time elapses, time elapses. I need a timer. The timer will have a clock input. And it will have output of T main green, T main yellow, T main red, T side green, so these 4 times are required so that we can go. and the timer will be started by a start timer. I should be able to start it. This is the clock. This is the timer. Fairly simple. What is equal to the controller? These times are going to the controller so that next sequence can take place. So if TMG is fed to the controller, the MG main green time is over, it should go to the next state. Once it is over, it should be detected and it should go to the next state. Side green, side yellow. This is the controller. Of course, clock is there. Here also. What should be the output of the controller? Start timer. So that we can always start next sequence. Fairly simple requirement for the controller and data path. Next is the ASM. We'll draw ASM. Four. Draw ASM. Oh, we will also give the controller outputs. Red signal, main green, main yellow, main red. Side green, side yellow, side red. But then main grid is automatically, when side is green or yellow, this is equal to main red. I don't need a separate signal. So the OR of this and this, side green or side yellow is main red. Similarly here, main green or main yellow, side red. So I don't need separate signals. I need only two OR gates, so this also is not required. So the controller has these inputs, these outputs. Data path has only one single timer and lights. Now we draw the ASM. I have taken too much space here, so I am going to write here separately. Main green or main yellow equals side red. Side green or side yellow equals main red. So after getting these two signals, I can OR them to get this. After getting these two signals, I can OR them to get these two. This signal. Now the ASM. Let us say it is the system is somewhere there and it starts. First, we'll say the main green state. Name of the state has to be put on the left hand top, and the binary values has to be put on the left, right. We'll do it later. Here, main should be green, right should be red. Then I will start a timer. Start timer can be done later. In this state, I will keep verifying whether PMG has reached. There is no, it continues to be main. If it is yes, it starts the timer. And goes to the next state, which I will call main yellow, side red. It is called main yellow state. Here I verify again the time. As TMY. Is the left? No. Yes. We go to start the timer. And goes another state. This is called this is called side green state. Here I verify. Whether TSG as a latch. If it is no, I continue to be here. If it is yes, I go to another state. This is going from here. I start the timer. And go to another state called side yellow. Going red. Start timer. and test TSY is a lapse. No. Continue to be inside with yes. You go back here. And then again it goes main green, side red and so forth. It goes on. You can stop it by switching off the power supply or whatever. That's what happens in the night. At the junctions, what they do is they switch off so that there's a flashing light. So originally it is in this flashing light mode. And somebody switches on, it goes to this state. So this is the specification of the problem. Continuing this also. This is specification of the problem as well as procedure, algorithm. This is, I will say, 1, algorithm, 2. I said 3 is data part, 4 is controller, 5 is ASM, and 6 is implementation of the ASM, implement of the controller. No, there are only 4 states. Simple. So let us call these states AB, 0, 0, 0, 1, 1, 0, 1, 1. 2 flip-flops will do the job. So next is ASM table. Present state will be inputs, next state A plus B plus outputs, zero, zero, inputs are to the controller. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, ADMG, TMY, TSG, TSY, and outputs are TMG, inputs are TMG, etc. Outputs are from the controller start, MG, main green, main red, main yellow, side green, side yellow. 4 lights and timer start. So when AB input is verified as TMG. TMG is verified. TMG bar, it remains in 0, 0. TMG is 0, 1. What lights are there? MG, SR. MG, SR. So MG is enough. All others are 0. Start, of course. This is first state. That is empty state. Then we have MY state. MY state is 0, 1. TMY bar is 0, 1. TMY is 1. It goes to SG state, which is 1, 0. Outputs are, but I can write all of them. Yeah, that's enough. Start timer. Here the output is MY. Zero, it remains in 0, 1. MY. So MY state is taken care of. TM is 0 or 1. TM is 1, we start the timer. Output in TMY state is MY. SR, I already said it can be obtained using MG and MY. So it's enough if I get MG, MY, SG, SY. 4. Next state is SR, SG. Next, SG state, 1, 0 state. Here we are monitoring time TSG. Not 1, remain in 1 0. Output is side green, no starting. If TSG is 1, then it goes to 1 1. State, output is still the same. Start timer. Finally, yes, yellow, side yellow, 1 1 state. You monitor TSY. If it is not 1, it is 0, remains in 1 1. If it is 1, it goes to 0 0. We go to 0 0. Output in this case is only 4 states, 2 flip-flops, A and B, and they go from state to state based on these inputs, and outputs in each state we know. So now, if you draw the hardware for time controller, ASM table is what is the number? Draw ASM 6 ASM table 7 controller design. So on the step, the last step. So here we have 2 flip-flops, flip-flop 1 and flip-flop 2. We'll call it flip-flop A, bar, B, B bar, clock, now this will be DA, input to flip-flop A, DB, input to flip-flop B. D input to flip-flop A, D input to flip-flop B. So I'll have 2 multiplexers, Mux 1, Mux 2, selectors from A and B, No, flip-flop is in 0, 0 state, two flip-flops, AB is 0, 0 state. We will only talk about A, which remains in 0. B, it goes to 1. It goes to 1 is TMY is on. It's always 1. It goes to 1 if TSY bar. This TMY, TSY are the outputs of the timer. Here, this is 1 if TMG is high. One if TMY is 0. This is 1 if TSG, and this is 1 if TSY bar. So you have the whole thing. The outputs can be drawn from here. Take A and B. Put it into recorder. To 1 max. 4 to 1 max. Now first is A bar, B bar. Out is MG. Second is MY. Third is SG. Fourth is SY. We already said MG or MY gives you SR. So MG or MY. MG or MY or gate. Side red. Similarly, SG, SY, or gate, green red. So all the 6 light signals. Starting at the timer is A bar, B bar, A bar, B, AB bar, AB. So it is start timer. A bar, B bar, TMG, A bar, B, TMY, AB bar, TSG, AB, TSY. This is how we start. So this, in every state we start the signal if the light elapsed time is 1. the 3 input gate. A bar, B bar, A bar, B, A B bar, A B is a decoder with TMG, TSG. So if you have A and B as the input to the decoder, 2 to 4 decoder, this is A bar, B bar, this is A bar, B, this is A B bar, A B. So this with TMG, I'll draw it there more neatly. Too crowded here. So the 4 output signals MG, MY, SG, SY are obtained. Combining MG and MY you get SR, side red. Combining SG and SY you get MR, main red. And starting signal is given by this equation. The hardware for that would be these are the 4 things, This is A bar, B bar. So I can take this 4, TMG, TMY, because this is same as the 4 decoder signals, A bar, B bar, A bar, B, A B bar, A B, A bar, B bar, A B, A bar, B, A B bar, A B. So I'm getting these 4 signals here right away. I'll use them. TMZ, TMY, TSG, this is TSY. So these 4 signals are combination. This is start timer. So we have accounted for all the signal outputs. 4 lights and start signal. Inputs are the timer. So this is the controller. Note that the clock is required for controller also. Clock is for controller also. And the architecture is timer. All we need is only timer. Start signal we give clock, there's a timer inside which counts. Outputs are TMG, TMY, TSG, TSY. All these 4 signals are required as input to the controller. See, every time I start the start signal, the clock starts from 0. So there's a counter inside. This is the actual timer, which counts the clock cycle. So every time you start it, it clears it. It clears and starts counting the clock. When a particular count is reached, TMG is reached, and then the next time the start signal comes, TMY, next time the clock TSG, etc. This is, and the other thing is lights. MG, MY, MR, SG, SY, SR into 2. Here we have MG, these are the inputs. Into 2 sets. That's all. System. Traffic light controller. This is a complete system design. Gives you overview of analog, combinational design, sequential design, drawing the architecture or the data path and controller separately, drawing the specification, clearly understand the specification, find out what are the components required, in this case timer and the lights, that's all. And then write the algorithm, step by step procedure. Then go to the ASM chart, draw the ASM chart completely, and then translate it into ASM table, and then go to the controller design, and then mark the outputs and combine the outputs in ways required to get the final output. For example, MG and MY to get SR, G and SY to get MR, and the start timer also goes from these signals and the timing. It's simple. Gives you an overview of digital system design problem. Sort of tells you what we have learned so far, what all we have learned so far, starting from the basic gate through the combination logic design, various components, multiplexers, gates, multiplexers, etc. Sequential logic, starting with the flip-flops. All that is used here in one place so that any digital system, real-life digital system, will have both combination logic and sequential logic. The combination logic drives the sequential logic based on the requirement of the problem. That is why I gave this controller data path model. Data path is what is available as signal processing elements, data processing elements, computers, architecture of calculator or computer. What are the building blocks? We have memory, we have arithmetic unit, etc. And then they should be activated. They should be made to work in a sequence required by the process, by the problem. So that is why you need the controller. So the controller gives the command signals to start and go a step-by-step procedure as required. But the controller cannot independently keep giving commands unless you know where it is, where the system is, what is the next step, So it gets back what is known as the status signal. So status signal is obtained from data path into the controller. Controller gives the outputs in terms of command to the data path. In addition, there may be external switch inputs like switch, starting, switch, resetting, power up, and outputs. External outputs such as clearing the signals, LED displays. System has completed the job. Okay. So we take two major examples. One is a multiplier, shift and add multiplier, the other is a terminal controller. Both are very good examples for this complete design of whatever you have learned so far from scratch, starting from lecture 1 to. Now it is up to you to learn or to try any system whose specifications are completely given to you. You go with the specifications, look at what are the components required, what are the control signals required, what are the components required may require signals. So signals required for the components. In this case, start timer. Start timer is a control signal. I should develop it, I should generate it. So I should go back and forth between data path and the controller. The controller should give all the inputs required to the data path, and data path should give all the outputs required for the controller. So for example, TMG, TMY, TSG, TSY are required here, and start timer is here, MG, MY, MR, the outputs are required here. So this is a unique combination of the two. Both are intertwined. So we have now completed the discussion of digital systems, starting from scratch all the way up to the design. So you should now keep trying. You can read textbooks. There are very good textbooks which give you other problems, more problems. And you should also try to do your own designs so that you have a complete understanding. You don't have to do always ASM. You can also do state machines. Or if it's only a combination logic, you can use multiplexers, programmable array logic, PROM, PAL, PLA, etc. Similarly, if sequential, without combination, you can have counters and things like that, registers, shift registers, and all that. With that, we complete the design process. I have two more lectures in which I will give you some extra things which are not essential but also will be required. So design is complete. You should now be able to do any design of your own. Next two lectures I am going to spend talking about some of the components, some of the concepts which are also important, which you have not been able to cover. Many books do not cover that, but I thought I will also do that. With this, I am going to stop today. Are there any questions? Anyone has a question can ask me.
No, sir.
Okay, good.